fundamental theorem of calculus. Again, much of this you're going to know, or it's going to make sense and it won't be difficult. If f is continuous and non-negative between a and b, then the area of the region bounded by the graph of f, the x-axis, and the lines x equals a and x equals b, so that shaded area down there, is equal to the integral, and we phrase this as the integral. I guess we should write out how we read this. The integral from a to b of f of x. The integral from a to b of f of x tells us the area. So that shaded area is the integral from a to b of f of x. When the integral has boundaries, it's called a definite integral. The boundaries are the a and the b. So that would be a definite integral. Without boundaries, no a, no b, it's an indefinite integral. We've done indefinite integrals. That's where we just took an antiderivative. So we're sort of familiar with this part of it. We have not yet seen what it means for those numbers. Well, maybe we've seen it. We just haven't done anything with it. Those numbers are where we start and where we end in terms of calculating area. The inside of the integral is called the integrand. That's the thing we're taking the integral of. The boundaries are also called limits of integration, or just the limits or the bounds. Kind of use those interchangeably, which is maybe a little bit confusing with limits, because limits has another definition. So it kind of just depends on the context. If we're looking at a definite integral and we say limits, we're talking about the a and the b. Okay, some properties of definite integrals. We'll walk through these, but I don't think these are going to be ones you have to memorize, because I think they're going to make sense. The integral from a to a. Okay, think about what this means in terms of area. So I want the integral under this graph from point A to point A. So it's like a line, but a line doesn't have any area. So that area is 0. So if the limits are the same, then you haven't really gone anywhere. There is no area to think of or to measure. The integral from a to a is 0. The next one kind of makes sense with everything else you know about math. If we switch a and b, if we flip a and b, flip the limits, you get a negative sign. That kind of fits with all the other things that, like a negative sign will flip the graph over in one way or the other, flips the number line. So the negative sign can be used to flip the limits. We use this frequently if we like the upper bound to be bigger than the lower bound, just because that seems to make more sense. We like to start at the smaller number and go to the bigger number. So if we want to flip them around, you can flip the limits, and the only cost is the negative sign. Right? If k is a constant, you can slide it out. If a, b, and c are constant, so number 4 starts to look crazy, but it's really not. If a, b, and c are constant, c is between a and b, then the limit, focus on the limits here. The limit from, this is not written right, the limit from a to c, oh it is, I'm sorry, it is written right based on those, I should draw out what it says. C is between a and b. So here's a, here's b. I got some area in there. And C is between a and b. Well, from a to b, that's the total area. From a to c, that's like this partial area, the area from A to C. And from C to B, And that would be the rest of the area. So it's just, I mean, it looks fancy with all those letters, but if you add up the two partial areas, you get the total area. And you can do that by breaking it up. So a to c plus c to b equals the whole thing. Occasionally it's helpful to split the integral into pieces if there's a value in there that's useful or helpful. Alright, 5, you've already used 5. You didn't know you were using 5. But when you did the integral of, let's say, x plus 1, you handled those separately, and you can do that with addition and subtraction. You knew that that was x squared over 2 plus x plus c. You can break up a plus or a minus integral. And the last one, the integral from a to b of a constant. Again, if you think about what this means in terms of area, so if k is a constant, and we go from a to b, then that area is just a rectangle with a height of k and a width of b minus a. So it's just an area formula. I would say none of those are really worth like memorizing. Did I miss you on that? None of those are worth memorizing. They're worth understanding and then knowing when to use them. Okay, speaking of when to use them and how to use them, let's work some example problems here. Evaluate the integral by graphing the function and using a geometric area formula. So the first thing we need to remember is that that integral means area from -4 to 4. So it means antiderivative, but it also means area. That's maybe the biggest deal of today, is that symbol means antiderivative. That's what you did on the most recent test. Like, we didn't do any area stuff. You did all antiderivatives. But it also means area under the curve. And in a little bit, we'll talk about how those two are related to each other. Okay, evaluate the integral by graphing the function and using geometry. Okay, absolute value of 2 plus x. Let's see, I remember what absolute value looks like, right? That's the v. Do you remember what a plus 2 in parentheses with x would do? My translation experts, which way would that move the graph? It's in there with x, so it's not up and down. It's to the left because the x stuff is backwards. If you don't remember that, well, then you just plot points and kind of figure it out. And a point you would definitely want to plot is -2, because that would get you 0. If you plugged in 0, you'd be at 2. Plugged in 4, we'd be up at 6. And then on the other side, because we need to get to -4, so the area we're looking for is this area under the curve down to the x-axis between -4 and 4. And probably the easiest way to do it is to just say, well, it's two triangles. Let's find the two triangles and add them up. So one triangle well, both triangles are 1/2 base times height. So 1/2, 2 times 2, form a green triangle. And then this bigger triangle, let's see, that's also 1/2 base times height. Let's be careful here. What's the base of this triangle? 6, because we started at -2 and went to 4. And the height of the triangle is also 6. So 1/2, 6 times 6. So half of 2 times 2 would be 2. Half of 36 would be 18. And 2 plus 18 is 20. So we just evaluated our first integral, our first definite integral, but we really didn't use calculus. We used calculus to know what was being asked, right? Calculus tells us we're being asked for the area, but then we used geometry to find the area, because that was easier than taking an antiderivative. All right, 2 is a little bit trickier. Do you know what shape that is? Well, some of you know. Let's see, if I started with y equals 25 minus x squared, if I squared both sides, and then I move the x squared over, just trying to get it back into a format you might recognize. What's x squared plus y squared equals 25? Pre-cal experts. Remember what shape that makes? X squared plus y squared equals 25. All of you students who had me last year. That makes a circle. Now we have to be careful when we get back to y equals, there'd be a plus or minus on there if we put the square root on there. This only has the plus, so this is like the top half of a circle. Or a positive semicircle. With radius 5. So let's sketch it out. So there's the area we're talking about. Area under the curve down to the x-axis. Well, that's half of a circle, so half of pi r squared. So half of pi times 5 squared, which is a good enough safe stop, but 25 pi over 2. Again, the antiderivative symbol also means area under the curve. And depending on the problem, sort of dictates which one you use. These first two are nice because they told you to use a geometric area formula. Sometimes they don't tell you, and you've got to figure out, well, is it easier to do an antiderivative or is it easier to do area? Both of these, it was definitely easier to do area because we don't know how to do an antiderivative of absolute value. Nor do we know how to do an antiderivative of that square root thing. Okay, so now some questions with a graph. The graph of f, composed of 5 line segments, is shown above. Integral from 0 to 3 of f of x. So again, that means area under f from 0 to 3. I'm trying to fit it all in there. All right, I'm not going to be able to draw all of these because they're going to be overlapping, so be careful how much you shade. But we'll shade a little bit. All right, so that's a triangle. We know the area of a triangle is 1/2 base times height. base is 3, the height is 2. So that gets me 3, but there's something weird, different, strange about that question compared to those previous two. Ben?
Why did you do it like above the lines of the
Okay, that gets to it. The question was why are we doing it like above the curve? Isn't it supposed to be below the curve? It's supposed to be below the curve down to the x-axis. But the trick is, like, a better way maybe is the space between the x-axis and the curve. But you're onto something here. Because it's below the x-axis, you want to guess how that affects my answer? It's going to be negative. It's flipped over. So that's weird, especially if you're thinking, wait, negative area, that doesn't make sense. So that's a negative area. That's weird to phrase it like that, but that's not a bad way to say it. It's the area, but since it's flipped over, and flipped over almost always means negative when you're in a math class, so that area is negative 3. Certainly the integral is negative 3. Yeah, be careful how you phrase that. I would not say that shaded area is negative 3. The shaded area is positive 3, but the integral is negative 3 because it's below the axis. Okay, from negative 5 to 0. Negative 5 to 0. At least we're above the axis on this one. I don't know. I feel like there's an easy way to calculate this area. Count the squares, right? Like, forget formulas. Count the squares. One, 2, 3 in the middle, plus a half on each end. That would be 4. Negative 5 to 0. All right, from negative 6 to negative 4. Negative 6 to negative 4. Ooh, what do we think? The area is negative 6 to negative 4. Okay, so my shaded orange area is 1. That is a true statement, but that integral means I need to think about positives and negatives. So why are you saying 0? Yeah, the bottom part is negative. So negative a half plus a half is 0. Part D, from negative 6 to 5. Oh, that's all the way. That might be a, like, add up the pieces thing. So, like, this is, how do we want to do this? We already have the pink triangles. So I'm going to say the first part is negative 1/2. I'm just going to add up the areas here. And then from negative 5 to 0, we said was 4. And then from 0 to 3 was negative 3. And then the last bit from 3 to 5. Need another color highlighter. Here we go. What's the area from 3 to 5? Or what's the integral from 3 to 5, I guess? Negative 1. The area is 1, but it's below the axis, so negative 1. And a lot of times students will start labeling these things as they find them. 0 to 3 was negative 3, so you can, when you go back to add them up, it makes it a little easier to keep track of things. So, that would be a safe stop, right? So if you don't want to mess up adding fractions, you're good. Let's see. 4 minus 4 goes away, and I'm left with negative 1/2 for that total area. What about E? What makes E different than D? Right, it's like backwards. I don't like starting at the bigger number and going backwards. So what I can do is switch that around. But that the cost of that is a negative sign would flip those around for me. Well, I already have that answer from the previous question. So negative half would be a positive 1/2. Number 5, absolute value. What does absolute value do to a graph or to a value? It makes them all positive. So I kind of need to go back and now add up my squares, but make them all positive. So I start with a 1/2, and my pink area already is positive, so that's +4. My green area was a -3, but now it's flipped over to a +3. And then that last little bit was a -1, but now it's a +1. All my pieces are positive because I flipped them all to the positive side of things. So 8.5, 8.5, 17.5, however you want to phrase that. That absolute value made all areas positive. Oh, I like question G. What's the area from 4 to 4? 0. Doesn't really matter what comes after that. There is no area between 4 and 4. So that's an easy one. H, the area from 0 to 5 of 4 times the thing. Let's just move the 4 out front. And then we'll count up our area from 0 to 5 and multiply it by 4.
We need to flip the 0 and 5.
No, because we like the lower number at the bottom.
Okay.
We like the lower number at the bottom. Start from the bottom and move it on up. So from 0 to 5, that would be -3 plus -1. I've labeled my triangle, so this, or my picture, so this is easier now. So that would be -16. All right, the last one, I think I'm going to split that up a little bit. 3, integral 0 to 5 of f of x, plus integral 0 to 5 of 2 dx. So f of x is the picture. This one I have to kind of draw on my own. There's 2, and I'm going out to 5. So I don't have a picture for the second part, but it's a pretty easy picture to come up with. So I guess we're going out of order here, but what's the area under 2 from 0 to 5? 10. So that second part is 10. Now, be careful, that did not come from my picture, or didn't come from the provided picture, it came from the picture I drew. Okay, area from 0 to 5 of the picture, that's -3 plus -1 again. So -12 plus 10 is -2. Integral means area, but yes, on the last test it also meant antiderivative. Here's the connection. This is the fundamental theorem of calculus 1.0. We'll do 2.0 tomorrow. The antiderivative of f prime. Hey, remember that was the last question on the test. I think everybody got it right. Congratulations. The antiderivative of f prime gets me back to f. On the test, it was just plus c because we didn't have limits. But now we have limits, so it's still f, but it's f of the, you evaluate at the top, evaluate the top limit, minus evaluate at the bottom limit. So take an antiderivative, but plug in the top minus plug in the bottom. Okay, well, let's do some. Evaluate each integral. Use proper notation in your work. We know we can't unintegrate or underive, a squared, so we have to square that out. So 4x squared minus 2x plus 1. We trust that people know how to square things. Okay, so let's take an antiderivative now. So let's see, 4x cubed over 3. Did I make the same mistake that they did?
Well, no, it's the middle term. I think you should make it.
That's what I get for making fun of people. Thank you for catching me. Now that's on film. I'd rather my mistake on film than somebody else's mistake, so that's okay. Let's see, increase the power by 1 and divide by the new power. And the antiderivative of 1 would just be x. Okay, I'm glad you said that. Because we are evaluating at 1 and 0, because we're going to plug in the top minus plug in the bottom, I don't need a plus c, because it would go away anyway. And this is what your notation looks like. So after you've done the integration, then this bar at the end means evaluate at 1 and then evaluate at 0 and subtract. It's the top limit minus the bottom limit. So if I plug in 1, I get 4/3 minus 2 plus 1 minus, if I plug in 0, I just get 0. Safe stop. There's our answer. All right, I'm glad you called me on the plus c thing. The indefinite integrals will lead to a plus c. That's part of why they're indefinite, is we don't know what c is. A definite integral, there's no plus c, because you're going to evaluate at the top minus evaluate at the bottom. I guess one way to say it is if you included the c, it would eventually go away, because you'd have plus c in the first one and then minus c in the second one, and they'd go away. So if you've got limits, you don't have to worry about the plus c. So now the trick will be, in a week when you don't have one with limits, will you remember the plus c then after we've ignored the plus c? That's pretty similar to one we did on the test. So this would be u to the 1/2 minus 2u to the negative 1/2. So this is more practice with antiderivatives. Increase the power by 1, divide by the new power. So 2/3 u to the 3/2. Increase the power by 1, that gets us to 1/2. Slowing down with the negative positive stuff here. Divide by 1/2, that's like multiplying by 2. So I get a 4 there. You could leave that as 2 over 1/2. It's just going to get uglier since there's more to do with this. In fact, there were a few people on the test who left them as u to the 3/2 divided by 3/2. And 2u to the 1/2 divided by 1/2. And that was okay. Like, that is an acceptable safe stop. But since there's more work to go, it's probably better to clean it up a little bit. Okay, 2/3, 4 to the 3/2 minus 4 times 4 to the 1/2. There's my first limit. Plug in the top, minus plug in the bottom. 2/3, 1 to the 3/2, minus 4 times 1 to the 1/2. And that is a safe stop. You can leave exponents and fractions and negatives and like that's calculator ready, like that's a safe stop. I do want to clean that up because on a multiple choice test, that's not going to be the answer choice. So do you remember what 4 to the 3/2 is, or how to figure that out? Flower power grows on top and the root grows underneath. So the root is the square root is 2, and then 2 cubed is 8. Square root of 4 is 2. 4 times 2 is 8. The ones are easy, so that's 2/3 minus 4. So let's see here. Let's clean this one up all the way. 16/3 minus 8 minus 2/3 plus 4. Let's see. I need a common denominator eventually. Just don't want to get it yet. 16/3 minus 2/3 is 14/3. Negative 8 plus 4 is minus 4. Now let's get a common denominator. So 14 minus 12 is 2. So my answer to all that is 2/3. Obviously, if that's a free response question, don't do all of that. Like leave it all written out like that. And almost everybody did that on the test. There was a few people on those Riemann sum problems. Like I wanted you to just leave them as the sum of the rectangles. A few people multiplied it out, and some of those were ugly with decimals, but a few people did it. They didn't need to, though. They should have left it like this. Number 7, antiderivative of secant squared. Antiderivative of secant squared. Let's see. That is one of the trig functions. So who has a derivative of secant squared? Tangent. So tangent of x. I don't need a plus c because I'm going to evaluate at the top minus evaluate at the bottom. So tangent of pi over 6 minus tangent of negative pi over 6. Plug in the top, minus plug in the bottom. By the way, on a free response test, that's a safe stop. You can leave trig functions as safe stops, basically because it's calculator ready and it's not calculus. Now that's not going to be the answer on the multiple choice test, but if it showed up on free response, you should probably leave it like that. Okay, tangent of pi over 6 is root 3 over 3, because I remember my unit circle. Tangent of negative pi over 6, maybe that takes a little bit more thought. Quadrant 4, so it's negative root 3 over 3. So 2 root 3 over 3. Number 8. You should recognize number 8 from Tuesday. 1 plus tangent squared. I'm pretty sure that's one of the Pythagorean identities, but I don't have those memorized. I only have sine squared plus cosine squared equals 1 memorized. If I want tangent to show up, I should divide by cosine squared. So let's see. Tangent squared plus 1 equals secant squared. Oh, so tangent squared plus 1 is secant squared. So I'm going to replace 1 plus tangent squared with secant squared. That's super convenient, because what can I do now? Those can cancel to 1. And so I thought this was a trig problem, but it's kind of just the area under 1 from 0 to pi over 4. See, I switched to doing area there. Although, I could also do antiderivative. Let's do both. Antiderivative, that's what we've been thinking. So let's keep it, I shouldn't jump to area yet. What's the antiderivative of 1? X. I don't need a plus c because I've got limits. So if I plug in pi over 4 minus 0, I get pi over 4. That's sort of the antiderivative way. The area way is to think about, let's see, the area under 1 from 0 to pi over 4. What's that area equal to? Pi over 4. So that one's a good one to remind us that that symbol means antiderivative, but it also means area. And it kind of depends on the problem as to which way to go. If you've got a nice geometry picture like the last page, then it's definitely area. If you've got an equation, it's probably antiderivative. If you've got a really easy equation, you could probably work it either way. Or you could work it either way. I'm looking back at the previous 3. I definitely could not do area for any of those other 3 because I don't know what that graph looks like. That's a parabola, but I don't know the area under a parabola. I have no idea what secant squared looks like. So usually you're doing antiderivative, but sometimes we sneak an area problem in there. All right, that's a lot of me talking. Let's get you talking. Jace, how about the antiderivative of 2t?
It's just t squared.
That is just t squared. Austin, the antiderivative of cosine?
Cosine.
And I don't need a plus c because I'm going to evaluate at minus pi over 2 and at positive pi over 2. Which one? On this one?
Oh.
You good?
I don't know. There was
So plug in the top one. Pi over 2 squared plus sine of pi over 2 minus plug in the bottom one. Oops, negative pi over 2 squared plus sine of negative pi over 2. That is a safe stop, but let's keep going. So pi squared over 4. What's the sine of pi over 2? It's 1 minus pi squared over 4. And the sine of negative pi over 2 would be negative 1. Let's be careful with our sign, with our SIGN out here. Pi squared over 4 minus pi squared over 4 goes away. What about the 1s? Do those cancel? No, they add. Negative, negative, so I end up with 1 plus 1 is 2. Which I don't know, seems like a weird answer, an easy answer. We got 2. That means if we did know the graph of this thing, the area under that curve is 2. Alright, last one. This looks ugly. I'm going to change that. See how many algebra steps I can do at once. I'm going to put the square root of 2 out front, and then make this x to the negative 1/2. Okay with that? Algebra. I have my stamps on my desk because when I was grading, some of you earned the algebra stamp. Now you're worried that you got the algebra stamp. Increase the power by 1, divide by 1/2, so that means multiply by 2, and then from 1 to 8. Okay, so that's 2 root 2 out front. 8 to the 1/2 minus 1 to the 1/2. That's a safe stop. But I don't want to stop there. That's boring. Let's keep going. 8 to the 1/2, that means the square root of 8. What does the square root of 8 become? 2 root 2. 1 to the 1/2, that's easy. That might be a multiple choice answer, but I feel like they probably distribute. So that would be 4 root 4 minus 2 root 2. That's a weird answer. They definitely would not leave that, because 4 root 4 is 8. Did I mess something up?
No, how did you get the 2 root 2 on the outside? I think all that.
Okay. The negative 1/2 I increased by 1 and got 1/2. And then I divided by 1/2, and that's where that 2 came from. Yeah, maybe it would have made more sense if I would have done x to the 1/2 with a 2 on it like that. That conceptually, that does make more sense. I think I probably should have done it that way. Okay, a little note to self. We can stop there. So today's assignment is worksheet 1. Again, the main thing is that integral sign means 2 things. They both start with A. Tell me again what the 2 words are. Antiderivative and area. And it depends on the problem which way you go. If it's a simple one and you can know the area, well then do the area. If it's a crazy looking thing that you don't even know what the graph looks like, well then you probably need to do the antiderivative.